All right, so as mentioned, my name is Abdul Isi. I'm the Engineer Technical Sales at Antec Controls. And for today's webinar, we're gonna go ahead and get into room pressurization solutions for critical spaces. So for today's webinar, we're gonna really focus on the room pressurization in applications like laboratories, hospitals, and pharmacies. And the goal here is to maintain safety, occupant safety within the space and the rest of the building. So we're going to review the requirements for room pressurization and space temperature control in each of these different critical spaces. So the learning objectives for this webinar is identifying the requirements for proper space pressurization, being able to distinguish between a negatively and positively pressurized space, being able to understand the different methods for performing space temperature control, being able to show an understanding of the different airflow control devices and their applications in these different critical spaces, and then lastly, being able to properly select and lay out your pressure controls for these applications. So for the agenda, we're going to go ahead and start off by talking about these applications and highlighting the requirements for laboratories, healthcare applications, and our compounding pharmacies. We're then going to go ahead and talk a bit about the different ways we can achieve this room pressurization with the controls. We're going to then get into the design considerations, and we're going to discuss the considerations for temperature control, airflow control, and the room pressure measurement, monitoring, and control. So with that, we're going to go ahead and get into it. So the first thing we're going to need to understand here before we get into the applications is understanding how can we achieve room pressurization. So essentially, room pressurization is just the direction of airflow movement from a clean space to a less clean space. So if you want to think about this, we're typically going to be designing these spaces and identifying where our hazard is. If your hazard is inside the room, you're typically going to want to ensure that airflow goes from outside the room to inside the room, which would be a negatively pressurized space. On the opposite end, if the hazard is outside of the room, we're going to want to ensure that airflow goes from inside the room to outside the room, which would be a positively pressurized space. So how we achieve this room pressurization is essentially maintaining a difference between our supply and our exhaust airflow. By maintaining this difference, we're able to pressurize the room based off of the transfer of the air and actually control the directionality of that transferred air. Now, what we're going to have to understand for these applications is how tightly sealed your room is and how much available leakage you have will actually dictate your ability to maintain and control to this pressurization. So on the right side of the screen here, we have a simple graph that actually shows the effect of your room leakage to the pressurization in space. So on the bottom of the graph, we have the difference of airflow between your total supply and total exhaust. On the y-axis, we have your pressurization in inches of water column. And then this red line is the actual impact of the leakage. So looking at that, the red line that offers 0.1 square foot of leakage, what you can see here is that a very small difference of airflow results in a very large buildup in pressurization. On the opposite end, if you have a room that has very high leakage at around 1.5 square foot, that's going to take us a lot of difference of airflow or a high difference of airflow to build up that same amount of pressurization. So what I'm trying to highlight here mainly is that we typically want to avoid having a room that's very tightly sealed because minimal differences in that difference of airflow can result in large changes in that room pressurization. But the opposite end is also true. If you have a room that's very leaky and has a very high leakage rate, it's going to take a very large difference in airflow for us to build that same pressurization. So the goal and intent here is that we want to be able to design a space that actually allows for leakage, but that gives us the ability to still control that room pressurization with a reasonable amount of difference in the airflow. So with this, we're going to go ahead and hop into the first application we're going to talk about, which is chemical laboratories. So again, I'm sure we've heard a lot about chemical laboratories today. So these are spaces where we're essentially equipping them for scientific experimentation, research, and education. And they're typically spaces that are utilizing airborne chemicals that can be harmful to people depending on how we are exposed to them. So there are a number of different types of chemical labs you're going to see. A common one you're going to see are synthesis labs, which are generally utilizing organic and inorganic compounds for research. Additionally, teaching labs are similar to synthesis labs, but they typically require the ability to accommodate larger groups. So here, it's really important to maintain an open line of sight so the instructor can actually see the spaces and the individuals as well to prevent potential hazards. Other chemical labs include biological laboratories. So these again are some of those BSL listed labs. So these are spaces that are conducting research on actual living organisms, and depending on those living organisms, they can actually be very, very restrictive due to the harmful actor or the hazard factor. And then lastly, we have hospital or clinical labs. So again, they're typically providing chemical or biological testing on specimens generally associated with patient care. So when we talk about laboratories, the things that we really want to keep in mind with these applications are the fume hoods. These are typically going to be one of the biggest driving factors in these lab applications. So typically there's going to be two styles of fume hoods. You're going to have your open bypass fume hood and you're going to have your closed bypass fume hood. So with an open bypass fume hood, these are typically constant volume hoods operating at a constant airflow set point. And essentially how the face velocity is varying is based off of the sash position. So as that sash opens up and it covers that louvered front panel, we're going to have more airflow come through the front of the sash. So typically these constant volume hoods are designed so when the sash is at the operating position, we're able to maintain the required face velocity set point and containment. The problem with open bypass fume hoods and constant volume hoods is the energy consumption. So more commonly these days, you are going to see most fume hoods designed with a closed bypass. So essentially what this means is the airflow will vary depending on the sash position. As that sash starts to open, the accompanying air valve or the accompanying airflow is going to increase in order to maintain our face velocity set point and essentially maintain our containment. So typically, again, these hoods are more commonly going to be more energy efficient because when that sash is closed, we're still able to maintain containment inside that hood while also reducing the airflow, essentially allowing us to save energy by having the fan operate at a lower set point. So the next application we're going to talk about is isolation rooms. So these are spaces that aid in the prevention of spreading airborne diseases to other patients, healthcare workers, and visitors. So the types of isolation rooms you might see are airborne infection isolation rooms, protective environment isolation rooms, and then lastly, an airborne infection isolation room with a protective environment. So we're going to break down the requirements for all of these different types of isolation rooms. So the first one we're going to talk about are the airborne infection isolation rooms, or alternatively called AII rooms. So these are spaces that have a patient with a communicable disease like smallpox, influenza, things like that. So these are potential diseases that can actually harm people in adjacent spaces of hospital, doctors, nurses, other patients. So we're going to want to ensure is that we're able to contain that airborne infectious disease inside that patient room. So typically with these spaces, you're going to see them negatively pressurized. So we're going to have airflow go from the corridor into the isolation room. So your total supply into the room is going to be less than your total exhaust leaving the room. On the opposite end, we have protective environment isolation rooms. So again, these are typically spaces where the patient has a compromised immune system. So an example of this could be a patient, potentially going under chemotherapy, a patient undergoing potentially who's been exposed to severe burns, things like that. They're in a state where any potential less clean air can really negatively impact their road to recovery. So with these protective environment isolation rooms, we're going to create this protective barrier by having the space be positively pressurized. So what this means is we're having airflow go from the isolation room towards the corridor. So the supply air into the space is greater than the exhaust air leaving the space. The last application we have here are airborne infection isolation rooms with that protective environment. So what this means is we actually have a patient now that has both a communicable disease but is also in a compromised state. So again, an example of this could be a patient who's been exposed to nuclear radiation. That radiation can actually affect other people who are exposed to it, but at the same time, their body is in a compromised state due to the effect of the radiation they're under. So in these kind of applications, we want to ensure that we're able to have a buffer room or anteroom that can sanitize the air between the corridor and the isolation room. So this can actually help us prevent germs from flowing into the corridor and affecting other people in the hospital. So the next healthcare application we're going to talk about is operating rooms. So again, these are spaces where we're performing a surgical operation and it's being carried out in a clean environment. So some examples of operating rooms can include a general surgery space, an emergency or trauma room, or an endoscopy space. So really the key item here for these operating rooms is that the patient can be in a sensitive space. So we're going to want to protect them from germs and less clean air from other areas of the hospital. So in this case, in order to create this protective barrier, we're going to positively pressurize the space. So we're going to have airflow go from inside the operating room toward the direction of the corridor. So again, we're going to have more supply air coming into the space than exhaust air leaving. The last application we're going to talk about here are compounding pharmacies. So these compounding pharmacies are different compared to your normal mom and pop pharmacy. And what these pharmacies are doing are mixing some of the more hazardous chemicals that can actually save a patient's life, like a chemotherapy drug, but can actually negatively impact the pharmacist who's mixing these drugs. So examples of some of these compounding pharmacies can include sterile or non-sterile spaces and hazardous and non-hazardous spaces. So the biggest thing here is we can be dealing with a sterile, hazardous pharmacy, a non-sterile, non-hazardous pharmacy, or any mix and match of those. All of these are going to have slightly different requirements. So again, we're going to want to rely on the standards to give us the design requirements of those spaces. So to look at just a couple of examples here, we're just going to focus on non-sterile compounding and sterile compounding spaces. So a non-sterile compounding space is a space that is where we're creating medication in a clean environment, but that space doesn't have to require to be completely free of all microorganisms. So these spaces are typically going to have a lower ISO class rating since we don't have to have them be absolutely clean from all microorganisms. On the other end, with sterile compounding spaces, these spaces now have to be clean from all types of microorganisms. So you're going to see them have a higher requirement for that ISO class rating. So again, with these spaces, typically depending on your configuration, be it a hazardous space or non-hazardous space, they have slightly different specifications for each. So the last one we have here is probably the more common type of compound pharmacy, and this is a shared compounding pharmacy. So what these spaces have is a cascading pressure relationship where we're now controlling the pharmacy between a common reference, which is typically going to be your anteroom. So looking at this looking at this compound pharmacy on the right side, you're typically going to have a positively pressurized mixing space, and you're going to have a negatively pressurized mixing space, and in between both, you're going to have an anteroom. So for these spaces, we're typically going to have pressure monitoring at each doorway to ensure that we're maintaining that pressure relationship between the positive space in the anteroom to the negative space, and then the corridor to the anteroom. You are also going to typically see door contact switches be recommended for these pharmacies, and this is to ensure that users are closing the doors to minimize disruption and fluctuations to that room pressurization. So now that we've talked about the applications that you may see in these critical spaces, we're now going to start to talk about the room pressure control methods. So there are typically going to be two main types of room pressure control methods. So the first we're going to talk about here is volumetric offset control. This is also known as flow offset control. So with these applications, we're maintaining a constant offset between our total supply air coming into the space and our total exhaust air leaving the space. So with these applications, as that room goes from occupied to unoccupied, heating or cooling, the goal is to maintain that fixed offset over time. And that allows us to build up that pressurization and allows us to build up that protective barrier. The thing to highlight though is with this volumetric offset control is that we're essentially controlling or we're building up that room pressurization independent of the actual room pressure set point. So we're not directly measuring the room pressure and making changes regarding to that. We're instead controlling to that fixed offset and allowing that to build up that room pressurization. Typically, again, volumetric offset control is most commonly going to be the more common applied approach in these critical spaces. You can still utilize room pressure sensing and door contact switches for application for volumetric offset control, but these will not be used for control. They're typically going to be utilized for monitoring purposes only. So to give you an example here, again, if the goal is to maintain a volumetric offset of negative 100 CFM, and if our supply airflow is operating at 1000 CFM, we're going to see that the exhaust airflow is going to operate at 1100, and that gives us our total, that gives us a room offset of negative 100 CFM. Again, if the door opens, the valves are not going to react to that change. They're still going to try to control for that negative 100 CFM offset. So the second application we're going to talk about here for that room pressure control method is direct pressure control. So again, these are applications where we're now directly measuring the room pressure and the air valves are reacting to those changes. So essentially over time, we're having the airflow adjust in order to maintain that constant fixed pressure set point. So in this case, we're no longer caring about what that fixed offset is. Instead, the goal is to maintain that constant pressure set point in the space. For these applications with direct pressure control, it is really important that you have a pressure sensor to give us the feedback on what that room pressure reading is, and then additionally having door contact switches. So if that door is left open, we're not trying to control the room pressure with the massive hole being the door being left open. So again, ANSI Z9.5 states that it is impractical to maintain your differential pressure while that door is open. And then ASHRAE 170 also states that, again, short-term excursions from the required room pressure relationship shall be allowed while the doors are moving open and closed. So again, as you can see here, if the goal is to maintain a constant room pressure set point of -0.02, we're gonna have the air valves essentially react to that. So in this case, we have 1,000 CFM of supply, we have 1,100 CFM of exhaust, and that gives us that room pressurization of -0.02. Now, if the door is open or left open, we're gonna have to make precisions so we're not reacting to that change. So ideally, if you have a door contact switch, if that door is left open, the valves are gonna hold in place until they close again. So next, we're gonna go ahead and talk about the design considerations for these critical spaces. So the first one we're gonna talk about here is the thermal consideration. So one of the biggest differences between critical space applications like healthcare and laboratories between your typical HVAC application is the order of priority. So typically in these critical space applications, our first goal is to be able to maintain safety in that space. If we can achieve and maintain safety in the space, now we can start to consider and maintaining that thermal comfort in the space. So again, I'm sure a lot of you are already intimately familiar with utilizing this equation in order to determine and calculate your thermal loads and your airflow rate from that. So what I'm mainly going to focus on is the different types of temperature control we can enable for these critical space applications. So the first one we're going to talk about here is the stage temperature control. So again, these are applications where the reheater coolant coil is operating between 0 to 100% before any additional airflow is added into the room. So the idea with stage temperature control is if we can maintain that room temperature set point with just the reheater coolant coil, that should be more efficient than having to have the airflow in the space increase as well. So with stage temperature control, this is typically a more stable form of temperature control because we're only utilizing one form of control. We're not modulating the coils and adding additional airflow at the same time. Now, if we were to do that, this would then be called synchronous temperature control. So what this means is as our reheater coolant coil modulates between 0 to 100%, we're having the airflow in the space modulate between the supply flow minimums to our heating and cooling maximums. So essentially, we're now doing two forms of control at the same time. The benefit of this is the speed. So we can actually achieve and maintain our temperature set point faster because we're adding more hot and cold air at the same time. The only thing you want to keep in mind though with synchronous control is typically we're going to want to keep in mind the speed of response because if it's too fast, it can cause issues. So you may need to slow down the temperature control loop to ensure that user comfort is still being maintained. The last form of temperature control we're going to talk about is the room temperature control with the DAT limits or discharge air temperature limits. So now what we're doing is instead of modulating our reheat or coolant coil based off of the room thermostat feedback, instead what we're doing is we're adding an additional layer of control by having our reheat and coolant coil modulate to maintain a supply discharge air temperature target. So the idea being is where we're controlling the room temperature based off of what the discharge air temperature set point is. The room temperature is too cold, the discharge air temperature set point will be high, and then as we start to meet the room temperature set point, we can actually lower the discharge air temperature target in order to maintain a stable response. Additionally, what we also gain with this form of temperature control is being able to set a high and low supply air discharge target. So this can allow us to then minimize any potential overshoot or undershoot in the system. So in an application like an operating room, where having stable temperature control is very, very important, utilizing a control method like this is very helpful. So the next thing we're going to discuss is the airflow control devices. So again, the two types of airflow control devices you're typically going to be used in these critical spaces are electronic pressure independent valves or mechanically pressure independent valves. The electronic pressure independent valves essentially will react, or the actuator will react, where there's a change in the airflow target and if there's a change in the duct pressure. So this can include terminal units or high accuracy terminal units. For mechanically pressure independent valves, instead, we have the actuator move when there's a change in the airflow target, not when there's a change in the duct pressure. So classically, this is going to be your venturi valve. The goal, though, when we're talking about these critical space applications, accuracy is really important. In order for us to maintain that user safety, we have to ensure we can maintain a high level of control. So typically, we're going to want to ensure that both airflow control devices that we utilize in these critical spaces can be accurate to 5% of the airflow. So either of these valves can be provided with a high speed or standard speed actuator, and it will typically allow us to get that accuracy we need. Now, with these air valve technologies, they can come in different configurations. So if we're looking at a constant air volume application, if we have a venturi valve operating in a constant air volume CV application, we can provide a venturi valve with no controls, no actuators, have the lever arm fixed in a constant position, and that valve will allow us to control to a constant set point. On the opposite end, if we have a high accuracy terminal unit, and if we wanted to control to the constant volume configuration, we're still going to have to provide a controller, we're still going to have to provide an actuator in order for us to have some form of control. Again, these valves need that electronic component to allow them to be able to control airflow independent of that pressure. If in case we want to be able to enable two-position operation with these air valve technology, for a venturi valve, we could actually provide it with a two-position actuator with a relay for feedback. So essentially what this means is for a venturi valve, we can provide it with a two-position actuator, have a control between two flow set points, and not require any controller at all. But again, if we want to utilize a high accuracy terminal unit to control to two separate flows, we still have to provide it with a controller, we still have to provide it with an actuator to give us that electronic pressure dependence. Lastly, if we want to utilize these air valves in a variable volume configuration, you're typically going to see both valve technologies have a controller and have an actuator. So that controller and actuator allows us to control the valve across its entire airflow range and gives us an accuracy within 5%. So the last thing we're going to talk about here before we open the floor to any questions is the differences between room pressure measurement, room pressure monitoring, and room pressure control. So depending on the critical space application you're dealing with, you may want to consider incorporating room pressure measurement, monitoring, or control. So in this section, we're just going to break down the differences between all three. And we're going to start off by talking about room pressure measurement. So what room pressure measurement enables us to do is just measuring the room pressure, the room differential pressure, and use that for a feedback mechanism that can be passed back to your building management system for reporting and analysis there. So typically with these applications, we're just providing a pressure transducer. That pressure transducer is measuring that differential pressure across the doorway, and then that gives us a feedback mechanism that we can report back. So in this case, we have a sterile compounded pharmacy. We have a pressure transducer installed between the doorways. So we have two mixing pharmacy spaces, and in the middle, we have our anteroom. And again, in this case, the transducer is giving us a feedback mechanism. And in the non-hazard and hazard space, we're measuring that room pressure in reference to the anteroom. If instead we don't want to measure pressure in this way, which we call a compound in a cascade way, we can instead have those pressure transducers measure the room pressure and then come back to a common reference. So in this case, we now have all three pressure transducers measure the pressure in reference to a common corridor. But in this case, we now have to account for changes in what's the acceptable pressurization in that hazardous space and that non-hazardous space. So in the hazardous space now, we require to maintain a negative 0.01 pressure, which allows us to build up that same pressure differential to the anteroom. And then in the non-hazardous room, we're now controlling to a positive 0.05 inch of pressure, which again still gives us that higher pressure relationship in comparison to the anteroom. The next application we're going to talk about here is the monitoring application. So these are applications where we have a device that's displaying and reporting what's measured. And then we have that display to give us that feedback mechanism. So whenever we're dealing with room pressure monitoring, the intent is to give us some sort of visual indication of room pressure. So this can be done with a ball and tube device or a mechanical pressure gauge, or it can also be done with a digital display. Some other considerations we want to keep in mind though is, does this pressure monitor, is it giving us local feedback? Is it giving us a remote feedback? Or are we able to actually monitor that pressure off-site, so without actually physically being in that space? And other options you may want to consider is differences with alarming, integration with your building automation system, if custom graphics are required, etc. So in this application, again, the same pharmacy application, we have our pressure display, we have our pressure sensor giving us that differential pressure across the doorways, and typically you may see a pressure monitor installed at each doorway. So each monitor is just measuring one differential pressure zone, and it's giving us a feedback mechanism before the facility staff enters into that space. Alternatively, if you want to limit how many displays there are, you should be able to provide a display that monitors multiple pressure zones. So in this case, we have a display that's monitoring a single display that's taking a reading from all three pressure transducers. Alternatively, we may want to have that display installed outside the doorway, so somebody coming into the room can see how all three spaces are maintaining their containment. And then lastly, we may instead want to provide a digital display that takes all of the readings from BACnet, but it also allows us to see some additional requirements. So things like temperature, air changes, humidity, things like that, and just have that installed at the doorway coming into the space. So the last application we're going to talk about here is room pressure control. So this is where we're now utilizing a pressure sensor in conjunction with a controller. So now the air valves can actually react to the changes measured at the transducer. It is optional in this case to have it come with a monitoring device. So it's not a requirement to have a monitoring device when we're wanting to do pressure control, but it's a very typical thing that we can see utilized. So the differences between room pressure control can be, let's say we have an isolation room example, we have a pressure measurement being measured, so a differential pressure at the doorway, and that's giving us that pressure monitoring feedback to the display. And then if we want to actually control the room pressure based off of the display readings, we're going to provide a signal so that the air valve can read what the room pressure is from the display and then maintain the overall room pressure control in that space. Alternatively, if we don't want to have a display in the space at all, but still achieve room pressure control, we can provide a room pressure measurement, have that connect directly to the air valve. So now you can still read the room pressure, but that's just being provided to the building management system. And then the air valves are still controlling to that room pressure. So based off the feedback we get from the display, we're now adjusting the air valves accordingly to maintain that constant pressure set point. So with that, that's everything to do with room pressure, these room pressurization applications. So we'll go ahead and enter into our summary and then open the floor to any questions. So again, with these room pressurization applications, we covered the differences in control. So we talked about the differences between volumetric offset control and direct pressure control. So volumetric offset control is most commonly used in most critical space applications, whereas pressure control we typically see used more in healthcare and pharmacy applications. Additionally, we see for temperature control, we covered the three that we typically will see. So either a stage temperature control where the reheat coil is modulating before any additional airflow is added into the space. We'll see synchronous control, which is again where the reheat modulates at the same time additional airflow is added into the space. And then lastly, we talked about room temperature control with those discharge air temperature limits. So this is where we're controlling that reheat coil to maintain a specific discharge air temperature set point. Additionally, we talked about the airflow control devices, which may depend on the application and project requirements. So a high accuracy terminal unit, we're directly measuring the airflow, and that's an electronically pressure independent valve. And then we have venturi valves, which are metering the airflow and are mechanically pressure independent. And then lastly, we finished off by talking about the differences between room pressure measurement, room pressure monitoring, and room pressure control. So with room pressure measurement, we're going to typically require a room pressure sensor to give us a feedback mechanism. For room pressure monitoring, this is where we now have a room pressure sensor and some sort of display. So it could be through the local monitor, a front end remote display. And then lastly, we have room pressure control. So this is where we're utilizing a room pressure sensor in conjunction with a controller to modulate the airflow to maintain that constant room pressure set point. In these applications, a display is optional if you'd like to use it. So with that, that's everything regarding to cover this webinar. So we'll go ahead and open the floor to any questions.
Thank you, Abdul. So Abdul, I actually just sent you a screenshot of some of these questions because one of them is a lot longer than the others. So maybe read through that when you get a chance.
Okay.
Well, so we'll address some of the short ones quick first. So in that last example, 1,000, and this was at 222, but at that last example, 1,000 CFM supply without 1,100 CFM exhaust, the offset would be positive 100 as negative room. Sorry, so in that last example, there's 1,000 CFM supply, 1,100 CFM exhaust, and yes, well, the exhaust would be offset would be positive 100, yielding.
Yeah, so in this case, how we typically will do this is when you're calculating your offset, you are taking your total supply airflow and subtracting it by your total exhaust airflow. So in this case, if the room is to be negatively pressurized, we're going to have 1,000 CFM subtracted by 1,100 CFM, and that gives us a negative 100 CFM offset. So essentially that tells us the room is negative by 100 CFM. So I think this might be maybe just more terminology, but I know some people will just say the offset as like an absolute and it'd be negative or positive, but in this case, we're saying that the room is negative and it's a negative 100 CFM offset.
There you go. Cool. Yeah, reading it the first time, I didn't really process what she's asking. Okay, sounds good.
Yeah.
All right, so
And then if
the
we take
next,
a look at the other one, yeah. Keep
Yeah.
going.
all right, so the next one is, okay, so do you have a sequence of operations available for the 3 different scenarios described in the thermal considerations slide?
Yeah, great question. So we do. So if you go to our Antec Controls website, we do have a master sequence of operation available. And again, if you ever have any questions about what application best suits to be utilized for temperature control, we can definitely help out with that as well. But typically, if we compare some applications, if the room itself doesn't have a ton of thermal heating loads, stage temperature control is probably going to be fine. If you have a space that has high differentiating changing and heating loads, or it's really important to have fast acting speed of response, synchronous temperature control is probably the sequence you want to use. And then if you have an application where maintaining temperature set point is very critical and minimizing overshoot, undershoot is really critical, or temperature fluctuations is really critical, you might want to utilize room temperature control with DAT limits. So if you do have any applications with Antec controls, we would help put this into your sequence of operation.
Great. And by the way, along those lines, at Buckley, we have a product specialist with Antec, and he'd be happy to work on any project-specific control sequences or the way that the system is laid out. So any of those questions you have during design, we'd be happy to answer to while you're, as support. So, okay, the last question is pretty long, so bear with me. I'm going to read this whole thing out loud. Possibly more relevant to the last session, but how long do the position sensors tend to remain accurate? My concerns are mechanical slop or carbon tracking. I'm not confident in 20-year-old Phoenix valves reading accurately, for example. We tend to only certify fume hoods, and they only look for the 100 feet per minute face velocity at sash height, not if the valve CFM matches a particular sash opening. Are retrofit kits available for older Phoenix pneumatic valves, 1990s vintage as well as newer ones? Do they use or replace all the Phoenix components, actuator, position, potentiometer?
Yeah, that's a great question. Was there anything else there?
That's it. But, and mind you, I did send you a screenshot of that one just in case you want to reference it again.
Perfect. This is a great one where we can probably follow up with you as well and provide some additional information. But I'll answer your question. You are correct in the sense of we do offer a retrofit kit for the Phoenix style venturi valves. These retrofit kits will replace the existing Phoenix actuator, controller, pneumatics, things like that, and potentially also provide an update to the potentiometer depending on the state of that potentiometer and the degradation it's gone through. Now, what we found in our experience is that the venturi valve design itself, if we're just talking about the valve, is actually very robust. So if it is operating in an application that it's designed for, so again, if it's a corrosive application where the valve is actually being able to maintain whatever corrosive flow it's going through without corroding, the valve itself is robust in its ability to maintain the lifespan of 15 to 20 years. So in this case, you kind of gain that advantage of replacing the valve technology with technology that makes it easier to service, be it for the facility side, the balancer side, or the startup and commissioning side. So I know you also highlighted a little bit there with like the slack and the slop of that valve, things like that. I know the older style, the much older style venturi valves that are in the market did have a little bit more of an issue with that slack causing inaccuracies over the lifespan of the valve. But with these newer style venturi valves, especially the ones that we provide Antec controls, they are designed to take that out. So again, you're not going to see the same issues of that valve losing accuracy when it's 10, 15, 20 years due to linkage slop in that case. But those really great question. Potentially we'll follow up with you and provide some additional resources that you can find on our Antec Controls website.
Awesome. Okay. Thank you, Abdul. That is the end of the questions for now, unless anybody would like to raise their hand and ask a question live. But if not, that's it. And that actually concludes our laboratory workshop. We really appreciate everybody's support and being here and tuning in and taking the time to learn about lab applications. Please keep the Buckley application, or I guess technical sales engineering team in mind as you guys design your systems. We are always here to support any project specifics you have, and we'd be happy to follow up with more information. We will be sending this a follow-up to this workshop, but you can always you can always look at the recordings of these on our website for future reference if you have any questions. So thanks again, Abdul. Thank you. And that's it.
It was a pleasure.
Cool. See you guys.